Welcome to this walkthrough of Jeeves on HackTheBox. This is box number 6 in our 10-box series of machines exploited without the use of Metasploit. We'll start off by running auto recon. And we'll let that run to its conclusion. You can pause the video here and we'll return when all the results are in. Alright, and the results are back. So having a look in our scans folder, we can see from the results that we've got a number of things open. Have a look quickly at the overall TCP Nmap results. We can see that we have a Microsoft IIS-based website called Ask Jeeves, running on port 80. We'll have a closer look at that in a moment. We also have looks like SMB shares in place with services on ports 135 and 445. We have a look further down. It is running SMB2 with message signing enabled, not required. So we're not looking at anonymous access, and certainly if we try SMB client and SMB map as we have in the past, both of those fail to authorize. So we're not looking at anonymous access there. We can try another route connecting to the Windows remote procedure call on port 135 using RPC client. So on port 135, I'm just trying to connect through to the IP. And it prompts us first password. Give it an empty password for now because we don't know it. And it tells us we can't connect to the server, that our connection was disconnected. So we're not accessing SMB through that. And lastly, we have another web service, HTTP, running on port 50,000. So two different websites on two different ports. So let's look at the one on port 80 first. And this is a search page for a local instance of the defunct Ask Jeeves search service. Well, it's not quite defunct, it's ask.com now, but it's probably not long for this world. In any case, no matter what we enter into this search field, we get an error message. Now this is a static error message that looks like it dates back quite some time, possibly as far back as 2009. So it's not being dynamically generated for our specific search. In a production environment, this is the sort of thing we might look to for information leakage that prompts additional tactics. So for example, this is an error for Microsoft SQL Server 2005, build 9.000 for an Intel x86 system. It appears to be trying to concatenate a string, this whole system information section, to an integer, and failing to do so, of course. So we know more about the SQL query that was attempted. We can see the Windows version, that it's for NT 5.0 on build 2195, Service Pack 4. We look down at the bottom, we get information about the Microsoft.NET framework and ASP.NET framework that it's using, 2.0.5727, etc. And it even leaks path information. So if we look into the stack trace here, we get information that there's a C drive, a web root folder, sock puppets within that, app code and user controls, and so on. So this would all be terrible if the search field actually did anything other than link to this old error message. In any case, the application would need to be fixed to correct this specific error, and it should be configured to only log errors and not display detailed stack trace information to the user. If we have a look at our GoBuster results for this port, we can see that really all we're getting is the basic index.html page, the search page that we saw at first, and the error.html page, which we're looking at right now. So there's nothing of interest here for the moment. If we have a look at our other website, we can simply provide the port after a colon. We get an interesting 404 message, problem accessing /dot. The reason is that it's not found. So it's giving us more information probably than it should. It should simply say, resource not found. So it's looking for a web page, but it has no default web page configured here. And this path information is being reflected on the page. So if we were to give it /test, it's putting /test on the reflected on the user's page. That suggests the possibility of cross-site scripting vulnerability, although some basic attempts with that show that the key characters like the greater than and less than sign are being sanitized through URL encoding. Some attempts at path traversal, trying to get further back into the folder structure, also come up unsuccessful. It is collapsing our ... slashes, but it doesn't bring us to anything below the base folder that it's attempting to serve up. Interestingly, though, we have no results in our GoBuster scan of this, our attempt to enumerate folders and files out of this. At least we don't get it from the basic auto recon scan, which uses the seclist common.txt word list, which is a smaller word list. So let's try a deeper list, the directory-list-2.3-big text word list. So here's our command here for GoBuster manually. We're looking for directories. We're looking at the URL specifically on port 50,000. We're going to give it the word list directory-list-2.3-big.txt. And we're also going to be searching for not just the directories, but also appending .text and .html and .php and so on to all of the words in this word list. So seeing if those files exist there as well. And we suspect that, well, text and HTML might be there, PHP might be there. We saw that ASP.NET was in use there, so ASP and ASPX might be in play, and we might have some Java. And we're going to output all of that in the place where we would normally have results. We didn't have any results, so we can just dump it out there. Let's close that quotation. And we'll give it a minute to run, and you can pause, and we'll come back in a moment. I'm also going to stop it prematurely. If you want to do the same, it could go on for quite a while, as we are looking for not just all of the directories in this big list, but all of the directories and all of the possible files that it could represent. So we'll simply stop it here, because we do have a result, and that is the Ask Jeeves directory. So we'll simply replace our /test with /ask Jeeves. Give it just a moment to load, and we get a dashboard for managing a Jenkins software and systems automation service. So we can see that we've got areas like people. We can see that there is a single user admin. We can see their Jenkins user ID. We can see that any builds that it has running, there's nothing at the moment. We have, more importantly, access to configuration, and management. So all of the management options on the site are completely open to us. The configure global security area has the authorization set to anyone can do anything. And if we really wanted to we could disable security altogether. Going back to the management area, we can see that we also have access to a scripting console, which allows us to execute arbitrary script in the groovy language for administration, troubleshooting, and diagnostics purposes. So a quick Google of for a groovy reverse shell. Finds this one in payload all the things. And we can simply copy and paste that into our Jenkins server script console. Before we get any farther, we'll set ourselves up a listener on port 9999. We'll update this script with our information, our attacker IP, and the port number that we are going to listen on. And it's going to create a reverse shell connection back to our listener and run command.exe. And we're in. So we've got a shell now at C users administrator /.jenkins. So obviously this is a major configuration mistake. This is a management service, and it should be locked down tight with least privilege accounts, long strong passwords, authentication to even load the website, access control rules allowing access from only specific IPs and devices should also be implemented. In any case, from our current shell, we can run who am I? Give it the /all this time to get a full set of details. And we can see that we're running as the user Kosuke on our Jeeves machine. The /all gives us all of the group information in the system as well as their privilege information. So if we navigate to their desktop, C users Kosuke desktop, and we can have a look at the contents there, and we have our user.txt flag. Although we did have access to the C users administrator /.jenkins folder, we don't actually have access to the C users administrator main folder. So we're going to need to elevate privileges to gain our root.txt flag. So we'll gather our system information for the Windows exploit suggester. We can actually see here that contrary to what we were told by the Ask Jeeves webpage, we're actually on a Windows 10 Pro machine. But we'll copy that information into a new file called sysinf. Next, we'll run the database update. And set our database to the current file. Give it the system info in our sysinf file, and let it determine what exploits are likely on this system based on the current patch settings. And right away we get back quite a collection of possible vulnerabilities on this system based on its version and patching history. So I did try the 41015 again without success. Provides an error message that the system cannot execute that specified program. Tried 41020 again, which we had success with in a previous machine for the region object integer overflow. That unfortunately just hangs the shell. And so the next one on our list is MS16075 based. It was a security update that Windows put out for SMB Server, and the exploit that it suggests right off the top is the rotten potato. So I located some additional notes on the rotten potato, on how to implement it. So we see that rotten potato uses the net NTLM v2 reflection between DCOM RPC and needs a privilege to impersonate security tokens SE impersonate or SE assign primary token. Apparently MS16075 fixed both vulnerabilities, and there is a variant called Juicy, which requires a CLSID string. I attempted the rotten potato, found that it does not work with this version of Windows, that is Windows 10 Pro. But as we see, we do have the Juicy Potato option as well. So let's try that. Now the rotten potato and the Juicy Potato exploits leverage that DCOM NTLM local authentication reflection. So the DCOM, or Distributed Component Object Model, is an integral Microsoft technology for communicating between software systems. The potato exploits cause the NT Authority system account to attempt to authenticate via NT LAN management, or NTLM, to a TCP port on the victim machine. And this port is monitored by the attacker's code. So this person in the middle opportunity allows the attacker code to locally negotiate a security token for the NT Authority system account. Now, if the attacker's current account has the SE impersonate or the SE assign primary token privileges, which allow a service to impersonate a specific user on the system, then the attacker can run programs using the token to impersonate NT Authority system. So if we go back and we have a look at our Who Am I results, we can see that SE impersonate privilege is indeed enabled on this user account. So Microsoft's MS16075 Windows update broke the original potato exploit, but other similar exploits, such as rotten potato and this Juicy Potato exploit, continue to work. And they will continue to work on Windows machines up to Win 10. Microsoft will not provide a security update for this vulnerability because the radical changes to DCOM would fundamentally alter the way in which services work. So the vulnerability won't be addressed until a future version of Windows. Now, it is possible to mitigate the impact of the vulnerability by modifying the permissions of users and service objects using DCOM config. That is, to remove those SE impersonate and SE assign primary token privileges from users that don't require them. The best current solution, though, is simply to protect sensitive accounts and protect any applications that run under service accounts. So let's start by grabbing the exploit code from its GitHub repo. It's at OHPE's Juicy Potato repo. And once we've got it onto our attacking system, we need to get it onto our target system, so we can run our HTTP server here. And we can retrieve it using some PowerShell. So this is going to execute in PowerShell the command opening a new web client, downloading the file from the location that we've provided, and saving it in the user's public folder because we're likely to have write permissions there. And we'll save it as tater.exe. So we can see we've gotten our GET request, and we go to C users public. Our tater.exe is there. So we execute the Juicy Potato code as follows. Tater.exe -t. So this is the type of create process call that it's going to make. There are two options. The T option for create process with token W, or U option to create process as user. It's irrelevant at this stage how they work. We're going to try both of them. So we're going to provide the star option to try both. -P is the program that we want to run with our stolen token. In this case, we're going to try the Windows command line. And we need to provide -L. So this is the COM server listen port. So this is where the exploit is going to connect to set itself as person in the middle during the NTLM token negotiation. It can really be anything we're not using. And we run it. We can see that it completed successfully, but we don't get a shell. We can't access the separate new command shell. So let's try instead to open a PowerShell reverse shell instead. Now this PowerShell reverse shell will rely on Nishang's invoke PowerShell TCP code. And the Nishang collection here includes shells. We're going to just use one of them, the invoke PowerShell TCP script. So I already have that on my machine. And what we're going to do is open that in our Sublime Reader. We're going to add, got the code here. We're going to add right at the end, invoke PowerShell TCP. We'll give it the reverse option. We'll give it our port number and IP address for yet another listener. And we'll save that as rev.ps1 in our home directory. So we can see that here. That's still being served up, so we can employ the same PowerShell command, only with our new file. So this is going to create a new web connection, download the file, revps1. Next, we need to create an exploit batch file for Juicy Potato to run revps1 in PowerShell as system. So the Juicy Potato will apparently only run a single command and doesn't seem to accept additional parameters, which we'll need in a PowerShell command on its own. So we need to create a batch file for that, so we can simply run the batch file. So the full command that we would need to run on the system is PowerShell. We're going to change the execution policy, or rather we're going to bypass the execution policy just in case there are any restrictions on who can run scripts, and it will run the command rev.ps1. So now we've got our exploit code in here, and we can copy it over as well. Okay, so we have all of the pieces in place. We simply need to set up a new listener on, this time, say port 9990, and run our tater again. So that we're still going to try it with both methods. The program we're going to try to run this time is exploit.bat. And our random port. Give it a moment. It's completed successfully, and we get a connection back. So now if we run Who Am I, we can see that we're running as NT Authority System, which means we are able to navigate to the administrators folder on their desktop. And we have access to the folder where root.txt would normally be. In this case, there's an additional challenge going on here. We don't have the root.txt, we have hm.txt. that tells us the flag is elsewhere and to look deeper. So we can have a look deeper for hidden files and folders. And we're in PowerShell, so we'll get child item. We'll look in the whole user's administrator path recursively for the attribute hidden. And that may take a minute or so. PowerShell I found on this machine runs particularly slowly. And we get lots of results back that are hidden from us. Desktop INI apparently is a hidden file across a variety of different folders. Some log files, and so on. We could have a look through each individual item in that list, but it will ultimately come to nothing, unfortunately. And rather than waiting for this process to finish, simply reconnect. And we're reconnected. So that really doesn't return anything. What we do know, though, is that we can hide data in alternate data streams in a file. So if we return to C users, administrator, desktop, which contains our hm.txt file, we know that we can check that quite easily in PowerShell with the getItem command. We provide it the path to the item we're looking at, and what we want returned is all of the data streams in that file. We can see that there are two. There's the main data, which was our look deeper, nothing to see here, look deeper, and an additional root.txt stream. And we can also quite easily get that out of our file using PowerShell, using the getContent command. Again, we pass it the path, and we specify the stream as the root.txt stream. And we get our second flag. So that's it. The first web page was potentially bad with its information leakage, but ultimately irrelevant for us in this particular case. Our deep search for open ports located our second website on port 50,000, and the basic GoBuster results from AutoRecon gave us nothing, which was a bit suspicious. So we simply needed to use a more exhaustive, extensive list of directories. And that found us the complete unsecured Jenkins server. Lock down that server, and the rest of our work here is much, much harder. Once into the Jenkins server, we were able to execute arbitrary Groovy scripts, which got us a foothold on the machine. The user that we were acting as had the impersonate and assign token privileges, which they probably should not. But that lets us run the juicy potato exploit, grab the system token, and impersonate system to run our shell command. So those sensitive user and service accounts also need to be locked down. Since Microsoft is going to be unable to plug that token impersonation hole until a future version of Windows, if ever, since their whole model for having services impersonate specific users relies on this exact sort of functionality. So in neither case did we exploit bugs per se. Both exploits relied on intended functionality, operating as intended, but in the hands of an attacker, this functionality has unintended results.